This puzzle completely goes against all human instinct. It even challenges the very idea of what it means to do math. It's a simple question, yet it took a 122 terabyte proof to solve. The final answer uses a basic pattern, but finding it required realizing that sometimes this pattern is guaranteed to break.
So here's how it works.
The colorful tiles may look random, but the numbers are following a specific rule. Tiles with a 1, for example, must be more than one tile apart, moving left, right, up, or down. The 2s must be more than 2 tiles apart. 3s must be more than 3 tiles apart, and so on. The overall diamond shape uses numbers 1 to 14. But what you may not realize is that hidden within it is an anomaly, a patch of squares where a certain pattern necessarily breaks down.
We believe, that this was not a thing that would arise. The number 1s here seem to appear in a chessboard pattern, except at one single point here and there.
That was Bernardo Subercaseaux. He's a PhD student in computer science at Carnegie Mellon University, and this quilt-like tiling is part of a mathematical question that he first saw in 2020.
There's a Facebook group that's called Actually Good Math Problems. And I saw a problem. I was like, wow, this is a really neat problem. I was at a summer school. I filled out these notepads while I was, listening to the talks with attempts to construct these coloring solutions. This was my sort of hobby at the time.
The simple tilings would end up completely transforming his perspective on what it even means to do math, and in many ways shape his research career, in which he's been developing and using new computerized techniques to solve numerous open problems with his advisor, Professor Marijn Heule.
I played with a lot of problems in the past, and this had kind of the flavor of something that should be within reach.
So what exactly were they trying to figure out this time?
Well, in our initial example, we used tiles numbered 1 through 14, but that was a pretty arbitrary choice. Why not 1 through 10 or 1 through 37, for example? The question is, what is the minimum number of different tiles needed for the infinite square grid? If you want to fill in every square out to infinity such that any 2 tiles with the same number are more than that number of tiles away from each other, how many different numbers do you need?
This innocent-looking problem would turn out to be so deceptively complex that it took a 122 terabyte proof to solve. That's over 100 times the storage space of your average hard drive. And the main reason why it was so difficult stems directly from what you see in that patch in the upper left of the diamond.
So how did they solve this problem? And what's so special about that patch of squares that it's worth hanging up the whole picture on the wall?
The cool part about this image is that little deviation from this very orderly pattern is kind of necessary to satisfy the restrictions of this problem. So that's why we really like it.
To start, let's look at a slightly different variant of the problem. In the original variant, we measure distance using only vertical and horizontal steps. So these 2 tiles with a 1 are considered 2 tiles apart. But what if diagonal steps also counted? Then those same 2 1s would be considered just 1 tile apart, and it would violate the distance rule. You would have to place the 1s farther away from each other.
So tell me about that other variant.
So the other variant, if you want to go from here to here, it's shorter to go diagonally than by doing 2 orthogonal lines. So not only changes the distance between a cell and the one immediately diagonal, but also between 2 far away cells, now it really shortens their distance.
This change makes tiling the grid strictly harder because tiles with the same number now have to be farther apart. But how much harder? After a couple weeks trying to figure it out, Bernardo discovered something remarkable. No finite number of different tiles could ever work. No matter how many different numbers you use, you'll always get stuck somewhere down the line. Incredibly, the proof of this fact can be summed up in a short, delightful argument. Take these 4 squares. Bernardo asked, what's the greatest number of 1s you can place here? You can put 1 at the corner, but try to place another 1 in any of the other 3 and it'll be too close to the first. Remember, diagonals are counted as adjacent now, so even if both 1s are at the corners, it breaks the distance rule. Since any block of 4 squares can have at most a single 1, it means the maximum possible proportion of 1s in the infinite grid is 1/4 of the tiles. You can do the same thing to find that the density of 2s is at most 1/9, since you can only put 1 2 in any 3x3 grid.
Suppose I place a number 7 here. I cannot place any other 7 anywhere in this grid, because even this one that looks to be the farthest away, it's actually still only distance 7 apart from it.
In general, with a k+1 by k+1 grid, you can fit at most 1 tile with the number k, since all of those tiles are within a distance of k from each other. A k+1 by k+1 grid has k+1 squared tiles, and we know you can place at most 1 tile with the number k within that grid. In other words, the maximum possible density of number k on the infinite grid is 1/k+1 squared. So can we cover the entire infinite grid? We have the maximum possible densities of each individual number, 1/4, 1/9, 1/16, etc. But if we add them together, their sum represents the maximum fraction of the infinite grid that could be filled in with all the numbers. So we want to see if this sum is greater or less than 100%. It just so happens that if you add 1 to the front of the sum, it's a famous series known as the Basel problem. And in 1734, Leonhard Euler showed that with infinitely many terms, it converges to pi squared over 6, which is about 1.64. So subtracting off the extra 1 we added, our sum is about 0.64, or 64% of the grid.
The total percentage that we get is actually smaller than 70%. Which means that no matter how we place things, the densities don't add up. They give you less than 100%, so you cannot cover everything with this.
And that was sort of the final resolution to this version of the problem.
Right.
Bernardo believes Euler himself, given this variant of the problem, would have reached the same conclusion. But the variant where only vertical and horizontal steps counted resisted the same analysis.
I believe you wrote something about Euler and this other version of the problem. Would Euler have been able to solve this problem?
We don't believe there's a short and nice argument. In the case of the problem we saw in the whiteboard, you can analyze the densities sort of separately. In this variant, you really need to go large and understand what is the joint density of not only 1 and 2, but of 1, 2, 3, 4, up to 14, for example. Even if you're like a genius like Euler that could come up with a solution to this very beautiful sum, that might still really not be enough to be able to tackle one of these problems.
To Bernardo, it was clear that solving this version of the problem was going to require an entirely different approach.
In the fall of 2021, Bernardo began his PhD at Carnegie Mellon University and met Professor Heule for the first time.
Bernardo came to you and he said, "Look, I have this really cool problem. Do you think we could solve it?" What was your response to that?
Oh, I'm very excited when students come to me with their own problem. When I saw this problem, I thought, oh, this is really cool, and I felt this should be doable. It's very hard, but I thought it was doable. Yeah, I immediately got very excited about it.
Heule is known for using computer-assisted methods to tackle hard math problems, and realizing this grid coloring puzzle might need such tools, Bernardo asked Heule if automated reasoning could help. Now, at this time, there was no plan that Heule would end up being Bernardo's advisor, but those plans were about to change.
I was originally planning on working on online algorithms for my PhD, but then Marijn Heule gave this talk on this problem called the Boolean Pythagorean triples problem, and he showed some pictures that had like colored grids. Immediately when I saw that, I was like, that reminds me of, this problem that I had thought of for a while, but, couldn't solve. He just said, sure, let's discuss it, see if it can work.
Heule specializes in satisfiability solving, or SAT solving for short, which is a computer technique for determining whether a set of logical constraints can all be satisfied at once. To understand what that means, let's take a look at this picture. Here we have 4 people who are trying to order a pizza. One of them wants at least one of their favorite ingredients, pineapple or bacon.
So the first constraint here is somebody who wants either pineapple or bacon. They're saying as a constraint number 1 that they want a pizza that has either pineapple or bacon, this being the logical or symbol. The next one, if they put bacon, then they get to add mushrooms. What they're saying is that either there's no bacon or there are mushrooms. So if there are mushrooms, this person is happy, but otherwise they want no bacon. The third constraint is a bit more interesting. So this person is saying they either want pineapple on the pizza or nothing else because they don't like the combination of pineapple with other things. They want either to have no pineapple, in which case, they might like a bunch of ingredients, or to have not bacon and to have not pineapple or not mushrooms. So here we're using 2 constraints to represent what the person said in only one in theory, but it's a cause of bringing things down to the logical world. The last one is somebody who doesn't like the mushroom-bacon combination. So what this means is that to make them happy, we can either not have mushrooms or not have bacon. Once we have this formulation, the question is, can I select for each of these variables, mushroom, pineapple, or bacon, some value, whether true or false, such that all my constraints are satisfied? And the answer in this case is yes. We can say no mushrooms, yes to pineapple, no to bacon. So some people will be hating on this, but that works. And we can check it here. So because pineapple is true, this part here is satisfied and is fine. Here, this is satisfied because bacon is false. And this is requesting as an option not bacon. So this part here is satisfied. Similarly, here not bacon is satisfied, and here not mushrooms is satisfied. And here we're being very generous with this person. We're satisfying both of the options that make them happy. So in this particular case, a pineapple pizza satisfies all the constraints.
A SAT solver is a computer program that would automatically figure out that a pineapple pizza satisfies everyone. Or in cases where logical constraints are not possible to satisfy, a SAT solver would make that determination as well. Ordering pizza was just a toy example, but many math problems can be encoded into logical expressions that a SAT solver can work with.
For our tiling question, constraints could look something like, it's not the case that there's a 3 here and also a 3 here, since those spots are fewer than 3 tiles apart. Another important rule is that each tile must be assigned one of the available numbers, as in no tile can be left blank. With a careful encoding, you can eventually represent all the necessary information about the tiling problem for a SAT solver. Bernardo and Heule did just that, first setting their sights on trying to tile a 72 by 72 grid with as few numbers as possible. But they wanted to do it in such a way that you could repeat the grid next to itself off to infinity and the tiling would still work. If that was the case, it would mean you could tile the infinite grid. There's actually a really slick way to modify the constraints to only consider solutions that can fit together periodically. To see it, first let's step down to a simpler example. Say instead of the infinite grid, we just wanted to tile this infinite strip. We could start by putting a 1 here. Then for the next tile, we can't put another 1 since it would be too close to the first one, so let's put a 2. For the next tile, we can put another 1 since it's far enough away from the first one. For the fourth tile, we can't put a 1 since it'd be too close to this one, and we can't put a 2 since it'd be too close to this too. There's only one tile in between them, so we have to use a 3. Amazingly, now you can just repeat these 4 tiles, 1, 2, 1, 3, 1, 2, 1, 3, infinitely on both sides, and it works. The 1s are more than 1 tile away, the 2s are more than 2 tiles away, and the 3s are more than 3 tiles away. But another way to think about this without having to reason about infinitely many tiles is that the first tile and the fourth tile are actually adjacent to each other, forming a loop. This simulates infinite copies of these 4 tiles on both sides. Notice that even across the ends of the loop, this 1, for example, is still far enough away from the other 1. Now for a grid, you can do something very similar. We want to put infinite copies to the left and right of the first one. So just imagine that all the tiles on the right edge of the grid are adjacent to the tiles on the left edge, enforcing the distance rule from the right edge to the left edge. And we can do the same thing to enforce the distance rule across the top and bottom edges, ultimately forming a donut shape. Using this trick, Bernardo and Heule found a solution, and incredibly, it used only tiles numbered 1 to 15. That meant not only could you tile the infinite grid with a finite number of different tiles, but you just need at most 15. Armed with the knowledge that 15 works, they started chipping away from the other end, proving that 12 numbers isn't enough. So that meant the answer was either 13, 14, or 15. But this is when Bernardo discovered something completely unexpected.
I was checking a general survey about different coloring notions. And it was formulated a bit differently, but it was the same notion. So at first it was like, this sounds kind of similar. It dawned on me that it was exactly the same thing, just like, written a bit differently. And then it was clear that several of the things that I thought we had proved independently were already known and in the literature. So that was a pretty bad day for me, I would say. I didn't know how my advisor was gonna react.
When other people are working on similar problems, I only get excited because then other people also think it's of interest.
Whether this meant that I had wasted a good part of the first year of my PhD, for example, working on something that was already solved.
That only puts the bar higher of where you want to get. Bernardo wrote me this email and he kind of felt a bit stressed. Other people have been working on it and they already have similar results. And I just got excited, okay, more people are interested in this and let's make sure that we beat them.
With a renewed sense of encouragement to keep making progress, they eventually optimized their techniques sufficiently to prove that 13 numbers isn't enough either. So the answer was either 14 or 15.
They believed that 14 also wasn't enough, that 15 was the answer they were looking for. But to prove it, they estimated that a 100 times computational speedup was necessary. They were going to need all the optimizations they could find. So they got to work.
What other authors did in the past, they take the square, so a square grid of certain size, and instead we used the diamond. And the diamond turned out to be much more effective, finite size to reason about.
Once they started using the diamonds, one nice improvement they were able to make came from realizing that there was asymmetry among many different tilings. For example, these partial tilings are essentially the same, they're just rotated versions of each other. You could also rotate and flip the grid in a variety of other ways to get equivalent tilings. In total, there are 8 different symmetries, and discarding the redundant ones, Bernardo and Heule could design their computer search to be 8 times faster than otherwise.
This initial symmetry breaking was a good start, but the extra efficiency gained from it alone was not going to be good enough to solve the problem. At some point, they were going to need a radically new idea. And after a few more months of hard work, they found it.
Originally, their encodings were built from statements about individual cells, what number goes in each spot. But the optimizations built into the SAT solver seemed to be taking a particular shortcut, representing the problem in terms of bigger regions. And this, as it turns out, would be the key to solving the problem. Instead of having variables that denote things like whether there's a 7 in some specific cell, now they could think in terms of whether there's a 7 somewhere in this bigger region. And you can combine those together. For example, if there's a 7 in this region, then there can't be a 7 in this region, since every square is too close for that to work. So why is this helpful?
Suppose, for example, you're trying to solve a crossword. You might have variables saying that in this cell, letter A goes, and then another variable that says in this other cell, letter T goes, and so on. So suppose they tell you, hey, here, the letter T goes there. If you receive that kind of advice, it's very helpful. But now suppose this magical oracle had told you instead, letter Q does not go there. It's 1 out of 26 possibilities you're discarding, so it's really not that helpful. But now imagine you have a different logical representation of the problem in which you have a variable that says the letter Q goes in this entire column of a crossword. If that variable is true, you know that Q is somewhere in that column. It's not as helpful as telling you precisely in which cell, but it is definitely still helpful. And what's interesting about doing this is that now suppose that variable is false. then I'm telling you the letter Q does not go anywhere in that column. That is more informative because it is discarding a bunch of cases at once.
That concept of getting information about bigger regions on a crossword puzzle applies exactly the same to the bigger regions of tiles we saw a moment ago. Now, there are a lot of different shapes they could have used for these regions, but their goal was to find a shape that was the most conducive to running a computer search in parallel, with hundreds of CPUs working on the problem at the same time.
People back in the 2010s proved that the Rubik's Cube can always be solved in 20 moves. That took 35 CPU years. But when people say that, they don't really mean they started running that computation in 1975, then waited until 2010 for it to finish. You had a lot of computers running that would total to 35 years. But that really might be a week of actual human time.
Eventually, their experiments led them to settle on using these plus shapes.
That plus encoding, how did you come up with that? Because it seems like such a strange thing.
We saw kind of what was happening and that the plus might be a good shape, but we tried a lot of different shapes, kind of everything that Tetris provides. And then we tried to see which works best, and the plus turned out to be the most effective one. Something that you figure out by trial and error.
They eventually got this in front of Donald Knuth, one of the most influential computer scientists of all time.
My advisor sent him the article and he was very pleased with it. And also read it very carefully and gave us a lot of feedback on, improving typos and stuff. So we're very grateful that he improved the paper quite a bit with his comments. Upon seeing this plus shape encoding, he mentioned that it reminded him of a cathedral, if I recall correctly, a cathedral in Norway in a city called Roa, R-O-A. Funnily enough, that happens to be my second last name, completely unrelated, and then Marijn was able to find on the internet a picture of that exact cathedral, sent it to Donald Knuth, and he was very amazed at what the internet can do in this sense, right? He had this vague memory of something he had seen many years ago, which is very impressive to me that he was able to recall, and indeed, it is the same kind of shape.
As they were making all their optimizations, Bernardo would start to pay extra close attention to something. In the tilings, the ones always seemed to form a chessboard pattern. And this makes sense. That's the closest you can pack them together without breaking the distance rule. So it seems like a good idea. Naturally, he conjectured that using a chessboard pattern of ones was the optimal choice for completing the tiling. He called this hypothesis the chessboard conjecture. If the chessboard conjecture was true, it would simplify the computational task by orders of magnitude, since you can just assume that the chessboard pattern of ones exists and fill in everything else around it. Bernardo and Heule quickly found with the SAT solver that if you do this, there's no way to fill in this diamond shape with only the numbers 1 to 14. You can't tile the diamond with 14 numbers if there's a full chessboard pattern of ones. And if a finite region isn't tileable, then the infinite grid wouldn't be either, since any finite region is just a subsection of the infinite grid.
So making the assumption that the chessboard conjecture was true, the number of different tiles needed for the infinite grid was 15.
Making this assumption, we could have the result, but we weren't sure if this assumption was actually justified. So I was trying really hard on paper to prove whether this assumption could be made without loss of generality. And and I tried, and obviously I failed because it's not true. But yeah, it took a minute to be able to actually see why it's not true.
Did you catch that? Here, let me replay what Bernardo just said.
I tried, and obviously I failed because it's not true.
The chessboard conjecture was not actually true. They figured that out by eventually finding that the same diamond shape, which could not be tiled with numbers 1 to 14 using a chessboard pattern of ones, could actually be tiled with numbers 1 to 14. But the only way to do it is if the chessboard pattern breaks down here, on the very edge. This was so fascinating to the two of them that Heule decided to make an art piece out of it, and I'm glad to have had the pleasure of being one of many visitors to lay eyes on it and share that same wonder. But of course, the art piece isn't the end of the story. We still don't know exactly how many different numbers you need for the infinite grid. Knowing that this diamond can be tiled using only 14 numbers instead of 15, you might think that maybe only 14 numbers are necessary for the infinite grid. But Bernardo and Heule weren't convinced. They still thought the answer was 15. However, because the chessboard conjecture was false, their task would be a lot harder than they were hoping, since they couldn't assume any sort of patterns to shortcut the search. Since this diamond shape was still possible to tile with 14 numbers, the plan was to use the next biggest diamond shape. But that added 60 more tiles, which might not seem like much until you realize that each of those multiplies the number of combinations to check by 14, since there are 14 different options per square. That's 14 to the power of 60 times more combinations. Luckily, the newest SAT solvers are often able to circumvent gigantic search spaces by taking a bunch of clever logical shortcuts, which researchers, including Heule, have been continually developing over the years.
After a few more months of optimizing, they were finally ready to run the SAT solver on this next biggest diamond shape. They accessed a supercomputer with 128 CPUs, ran them all in parallel on the problem, and taking 4,851 CPU hours, a couple days later, the computer outputted a 122 terabyte proof.
The answer? It's impossible to tile that next biggest diamond with only 14 numbers. That meant the search was over. You need all 15. There's something remarkable about this story, which is that there seems to be this very natural pattern that arises out of the tilings, the chessboard pattern of ones. And as humans, our intuition guides us to believe that patterns we observe on a small scale will hold on the larger scale. But that's not always true.
It's a fantastic thing, in my opinion, that you can have mathematical intuition about what you expect to happen, and the computer ends up telling you you're wrong. You think that you can come up as a human with these nice patterns that must always hold, but it represents, in my opinion, pretty well with just one image that sometimes you do need to deviate from the pattern.
Interestingly, the tiling solution for the infinite grid using 15 numbers does in fact still use a chessboard pattern of ones. But besides just being a curious mathematical happening, the fact that the chessboard pattern has to break down when tiling this diamond with 14 numbers also has profound implications for what it even means to do math. If the chessboard conjecture had been true, it would have made the problem almost trivial, as you could fill in half of the squares in advance, and you might have been able to solve it the old-fashioned way, with pen and paper.
If this conjecture holds, then you can probably have other conjectures and maybe solve this problem by pen and paper. But because of this very large counterexample for this conjecture, none of this can work, and so it's very unlikely that a pen and paper proof exists that actually shows that the number is 15.
Right, because that was the smallest counterexample, and yet how many squares does it have? It's a diamond of size 14.
Yeah,
So people can do the math at
people
home.
can do the math, yeah,
Yes.
so yeah.
Part of me is actually happy that this showed up, because I think it's nicer to take a bit longer but show that the problem is a bit more nuanced than it could have been. Retrospectively, I'm pretty happy that there happened to be this nice obstacle along the way.
Now, earlier in the video, we saw how a very similar variant of the problem could actually be solved with a short and elegant proof with pen and paper. It involved analyzing an infinite sum that Leonhard Euler figured out in the 1700s with pure human creativity. But it's unlikely that even a genius like Euler would have been able to solve the original variant.
Euler could have potentially come up with a solution with 15 colors. But in order to discard 14 colors, I do have the feeling that there might really not be a short human way without computers. You really need to understand how sort of everything interacts, and that interaction shows at a very large size for a human to analyze.
Now, you might think that this phenomenon would only apply to pure math problems. But the magic of SAT solvers is that optimizations intended for solving these puzzles often indirectly translate into more general improvements to performance. For example, the plus encoding which they had used to improve the potential for parallelism turned out to be a representation of a broader idea, which Heule and a couple graduate students later implemented in a more general form.
In 2023, so after we solved this problem, these students implemented a more structured version of this, and they submitted it to the competition, and they won that competition. This technique, now called structured bounded variable addition, is practically used by all the top tier solvers now. And not only useful for this specific problem, but also for many other problems as well.
Problems that people are, publishing a solution on are sometimes a metaphor for a way broader class of problems. But every once and then, the techniques you develop for the metaphor really carry out to real problems that people care about. And graph coloring is kind of an example of a problem that really might sound like an odd mathematical curiosity that has no application. But graph coloring really does have many practical applications.
Solving hard mathematical puzzles seems to translate into more general improvement to performance.
There's definitely a lot of truth to that. You would expect that a technology that is dedicated for each problem would be more effective. This technology is being made for general use and somehow very effective.
Most people would probably never even think of a gargantuan computer search when they think of doing math. There's often a strong cultural preference for simple proofs, and Bernardo used to share that preference.
I think I just had a much more rigid and juvenile view of what mathematics is. This was like a first gaze into knowing that there was much more. It really broadened what I thought was to do mathematics. You might as well forget, at least at first, about what is the most elegant proof, for example, but really try to exploit all the possible resources and ways you might be able to solve the problem. And then computers are a fantastic tool. A Danish mathematician called Piet Hein, he says something like, problems worthy of attack prove their worth by fighting back. To me, that picture here represents a bit of that. It was like, the problem sort of coming back at us and saying like, oh, you thought that, it's going to be this easy and that you could, enforce this pattern. And the truth was that it was not guaranteed to be there. So to me, that was one of the ways this problem proved to be worthy of attack.
A good puzzle, as Bernardo says, is often a metaphor. And I think one of the reasons why solving puzzles is so important is because they push us to try new ideas and think in ways we normally never would. The hardest puzzles to solve are often the ones that lead to progress in unexpected ways. Problems worthy of attack prove their worth by fighting back.
If you enjoyed this video, I'm sure you'd love this one that I made with Professor Heule about a 100-year-old geometry problem that he helped solve. Special thanks to Bernardo Subercaseaux and Professor Marijn Heule for their contributions to making this video, and to Professor Heule and CMU and my Patreon supporters for funding the video. If you're interested in having your research featured on PurpleMind, reach out to me at my email in the description below. Thanks so much for watching, and I'll see you next time.